In the previous video lectures, we have seen the logical instruction sets. There are 3 instruction sets remaining. We will see that now. The instruction that are remaining is rotate instructions. So using 8085 microprocessor, with this instruction, we can rotate the value in the accumulator. So the first instruction is RLC, which is nothing but rotate accumulator left. So this instruction rotates only the value in accumulator. It won't rotate the values in the other general purpose registers. So what will happen is, so accumulator is how many bit register? It's an 8-bit register. So it will rotate the 8-bit values within the register itself. So we will see it with an example. So this is your accumulator register, and this is the carry bit in flag register. So what will happen is, the instruction says you have to rotate the accumulator towards left. So towards left in the sense, by this way you have to rotate. So what will happen is, the value in 7th bit is shifted to 6th bit. So this will be shifted to 5th, and 5th will be shifted to 4, 4 to 3, 3 to 2, 2 to 1, and 1 to 0. Okay. So now the 0th bit will be given to the 7th bit as well as to the carry. So this is how the rotation happens. So consider that accumulator is having the value 5A. Okay, 5A, what's the binary BCD value for 5A? 5 value is 0, 1, 0, 1, and A value is 1, 0, 1, 0. So this is the value in accumulator, and assume that carry is having the value of 1. So when the processor executes this instruction, RLC, rotate accumulator left, what will happen is, so bit number, this is the accumulator register, and this is the carry. So before executing this instruction, carry is having the value of 1 and accumulator is having the value of 5A. After executing, what will happen? The value 0, here the value 0 will be shifted to 6th bit. This one will be shifted to 5th bit. This value shifted to 4, and this is shifted to 3, this is shifted to 2. This is shifted to 1, and this is shifted to 0, and the 0th bit is now given to 7th bit, that is 0 will be shifted here, and as well as it is given to carry. So now what's the value? BCD value, carry is having value 0 and accumulator is having the value 2C. It's not C actually. So it will have the value 2D because 12 plus 1. Okay. So before execution, accumulator has the value of 5A. After execution, which means after shifting it towards the left, it has the value of 2D. So this is how the rotation takes place. The next instruction is rotate accumulator left, that we have seen. Next instruction is rotate accumulator right. Next instruction is rotate accumulator right. So in the previous instruction we have rotated the accumulator value towards the left, and now in the previous video lecture we have seen about the logical instructions. In that 4 instructions are remaining. Those instructions are belongs to rotate instructions. So first we are going to see about rotate accumulator left. RLC. So this instruction rotate the value in accumulator towards left. It won't rotate any other register values. So for example, this is your accumulator register, which is of 8-bit. So this is the carry bit in flag register. So what will happen is the value in the accumulator register will be shifted towards the left bit by bit, which means the value in the bit number 0 will be rotated to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. So then the 7th bit value will be transferred to the carry as well as to the 0th bit of accumulator register. Let us see this with an example. So before execution, consider that accumulator register is having the value of 5A. So the binary BCD value for 5A is 0, 1, 0, 1, A is 1, 1, 1, 0, sorry, 1, 0, 1, 0, and assume that carry bit is having the and assume that carry bit is having the value of 1. So after execution, what will happen? So this is your accumulator. So what will happen now? Towards left, in the sense the value in the bit number 0 is transferred to 1, 1 to 2, 2 to 3, 3 to 1, sorry, 3 to 4, 4 to 5. Okay, 4th bit value is 1, that is shifted to 5, and 5th bit value is 0, that is shifted to 6, and 6th bit value is 1, that is shifted to 7, and 7th bit value is 0, that is shifted to carry and as well as to 0th bit. So what value we will get after shifting? So this is B and this is 4. So after execution, accumulator is having the value of B4, carry is having the value of 0. Okay, now you got it how the rotation works. So the next instruction that we are going to see is rotate right the accumulator. So the instruction is RRC. So in the previous instruction we have rotated the value of accumulator in the left direction. So now we are going to rotate the accumulator in the right. So this is carry. So we are going to rotate right. So how this happens? The value in 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1, 1 to 0. So this 1 is given to carry as well as to 7th bit. So we will consider that before execution, we will consider the same value 5A that resides in the accumulator. Carry is having the value of 1. So as we have taken the value that we have used in the before instruction itself, So when it is rotated towards right, what will happen? So now we are rotating towards right side. So the bit number 7 value is given to 6. So 6 value is given to 5, 5 value is given to 4, 4 value is given to 1, sorry, 4 value is given to 3, 3 value is given to 2, 2 value is given to 1, first bit value is given to 0th bit, and 0th bit value is given to 7 as well as to carry. So now after execution, what value will be stored here in the accumulator? So this value is 2 and this value is D. So 2D will be stored in accumulator and carry you are having 0. So this you are rotating the accumulator towards the right direction. So the next instruction that we are going to see is we are going to rotate the accumulator towards the left, but the difference with the previous is we are going to rotate it with carry. So previously we didn't rotate with carry, we are just rotated the accumulator only. Now we are going to rotate with carry. So we will see how it happens. The instruction is RAL, that is rotate accumulator left through carry. Fine. So it will be like same as before. You are having an accumulator register. This is your accumulator. And this is your carry bit of flag register. So now we are going to rotate left side this way through carry. So what will happen now? The value in 0th bit is transferred to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7. This 7th bit is given to carry and carry value is given to 0th bit. Previously what we did, the value in 7th bit is given to carry and as well as to the 0th bit, but here bit number 7 value is given to carry and the carry value is given to 0th bit. Okay, we will take an example. So before execution, accumulator is having the value of 5A. We will consider the same example as previous. So and carry is having the value of 1. For example, I am saving. So we will have that same value. So after execution, what will happen? Sorry. We are going to rotate left through carry. So the bit value 0 is given to 1, 1 is given to 2, 2 is given to 3, 3 is given to 4, 4 is given to 5, 5 is given to 6, 6 is given to 7 and 7 is given to carry and carry value is given to, okay, this is how, and carry value is given to 0th bit. So what's the value? The carry is having the value of 0 and accumulator is having the value, take this, B5. Okay, this is B and this is 5. Okay, now this rotation happens through carry. Carry value is included here. So the next instruction is rotate right, rotate accumulator right through carry. Okay, so the same scenario. Okay, here what happens, you are going to rotate right. This way we are going to rotate. How this rotation takes place? 7 is given to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 1, sorry 3 to 2, 2 to 1 and 0. So next 0 value is given to carry, carry value is given to 7. So consider with an example the same value 5a and carry value, now we consider that as 0. So what will happen? 0 1 0 1 0 1 0, carry is having 0. So after execution, what will happen? 7 to 6, 6 to 5, 5 to 4, 4 to 3, 3 to 2, 2 to 1, 1 to 0. Then 0th bit is given to carry and carry value is given to 7th bit. So what's the value? After execution, carry is having the value of 0. And now what value does it have? This is 2 and this is how the rotation takes place. So that's all about logical instructions, and next we will see about the branch instructions. The branch instructions are used to change the sequential execution of a program. So for example, if you are executing 4 lines in a program, if you have included a branch instruction in between with some memory addresses, automatically a processor will jump to the memory address what you have mentioned there. Fine. So we will see that with an example. So before that, the branch instructions are of 3 types. One is jump, another one is call and return, and third one is restart. Using these instructions, that is jump, call or restart, you can disturb the normal execution of a program and you can jump on to another location other than the program where we have stored. So first we will see about the jump. So the jump instructions are of 2 types. One is unconditional jump. And second thing is conditional jump. First we will see about unconditional jump. So example for unconditional is JMP and you have to mention the 16-bit address. That means memory address. So if you have used jump 2000 in the sense, the processor once it has seen this instruction, it will jump to the address 2000 and execute whatever the instruction that you have stored in 2000. We will see it with an example. Okay, so you are having a program like this. Okay, so just leave the explanation of this program. We will concentrate only in the jump instruction. Fine. So consider that you are having this program in this address location 4400. So your processor is executing this instruction line by line. So when your processor execute this instruction add B, which is in the address 4409, what value PC will have? So PC is nothing but your program counter, which stores the address of the next instruction to be executed. So the next instruction for this add B is jump 5500. The address of this thing is 4408. This we will have in PC when your processor is executing this instruction. Fine. So when after executing this instruction, when processor comes to this instruction, your PC value will be this one, 4400, not 4. Okay, but when your processor sees to this instruction jump to 5500, we didn't mention any condition for jumping. Once your process sees this instruction, it will leave the execution here itself and jump to the address 5500, and it will execute whatever instruction we have here. Suppose if we have the instruction like this, for example, I am saying if you have the instruction like this, it will start to execute the instruction from this address till the end. Okay, fine, till the end it will execute this. So once this end is over, it will return to this instruction. So how it knows? It has to come to this, so it will knows from the stack. Fine, that we will see later how it returns. So now you just know that once the process comes here, what it will do, it will literally jump, stops the execution here itself. It won't execute these lines, it literally stops execution and jump to the address 5500. Fine. So this is how the jump instruction works. So next we will see about the conditional jump. So conditional jump is same as unconditional, but the thing is, before it jumps, it has to meet some condition, or it has to meet or satisfy some conditions. If it's satisfied with the condition, it will jump to that particular address. For example, if the condition here is JC is nothing but jump on carry. Okay, fine. So consider the same example as here. Instead of jump, we will have same example. Instead of jump, we have JC 5500. So when your processor come to this line JC, what it will do is, it will 5500. Your processor will check to carry bit in flag register. Fine. So which is nothing but the 0th bit. Fine, this is the carry bit of flag register. Now it will check if this carry is set, that is jump on carry. If it is 1, then it will jump to the address 5500, otherwise it won't. It will continue with the normal execution of the program. So you got it. So if the condition is met, it will jump to the address that we have mentioned in the instruction. Otherwise, it will continue with the instruction that follows the program. So as like jump on carry, other conditional instructions are there. They are J and C, which is nothing but jump on no carry. So JP, which is nothing but jump on positive. JM, which is nothing but jump on minus. If your value, if your 7th bit of flag register is sign flag. So if it is 1, which means that the value is negative. If the value is negative, it will jump. Fine. So next thing is jump on 0. Next thing is jump on no 0. Another one is jump on even parity. PE means even parity. And next thing is jump on odd parity. All these instruction will check to the flag register. So if that particular bit satisfies, if it is set, it will jump, otherwise it won't jump. In this case, if the carry is set, it will jump, otherwise it won't jump. But here the case is jump on no carry. If the carry is 0, then only it will jump, opposite to the previous case. So if the carry is 1, it won't jump, it will continue with the program. So that is what about unconditional and conditional jump. Next we will see about the call and return instruction. So call is also of two types, one is conditional call and another one is unconditional call. First we will see about the unconditional call. So as of jump, the syntax is call, then you have to mention the 16-bit address. So what this instruction will do is, for example, if we have call 4500, once the process sees this instruction, it will jump to this address and executes the line. It will jump to this address 4500 and execute whatever the instruction that we have here. Fine. We will see the unconditional jump with an example. So take this as an example. Again I am saying don't see into the internal operation of this program. Just we are going to concentrate about the call instructions only. Fine. So this is an example, and here we have used, this is the flow of the program. Here we have used to call 6500. Fine. So as we discussed before, when your processor executes this instruction add B, PC will have the address of next instruction, that is nothing but call 6500. Okay, the PC value here would be 4608. Fine. So when the processor executes this line at the start of executing, fine, at the start of execution, PC will have the value of this instruction. Okay, it would be 460B, but when at the end of execution, the PC value would change to 6500, because the call instruction, what it will do, it will transfer the processor execution from this address to 6500. Fine. So before it jumps to 6500, what will happen is the value of the PC, so before it has 460B, no, so that will be stored in the stack. So why it's stored in the stack? In the sense, so when it jumps to this address, after it will execute the lines here in this line till the end. At the end, it should return to the address where it left, because the execution stops here. So after executing this, so it has to return to the address where it has left. So at the time we should store this in the memory, no? So for that case, the value of PC, because we should know the return address, so the value of PC will be stored in the stack. So stack is nothing but is just like the memory we have. So it will store in the top of the stack. The top of stack value is stored in stack pointer, right? That we have seen in the architecture. If the stack value is 3500, for example, so at 3500, what value will have is, so we have already seen that each and every location is of 8-bit. So but the address value that we have is 16-bit. So 8-bit it will be stored here. At 3500, the lower byte of PC will be stored. So the lower byte is nothing but 0B. It will be stored here. So then the address is 3501. There the higher byte of PC will be stored, that is 46. So before it jumps to 6500, what will happen? PC value will be changed. So that will be feed with the address in the instruction, and PC lower byte value will be stored in the stack pointer -1. Actually, I'm sorry if my address is 29FF. Okay, sorry if my PC values 3502, it will be subtracted -1, then the higher byte value will be stored, then -1 lower byte value will be stored. Okay, fine. So the PC's higher byte value will be stored in stack pointer -2, which is nothing but, if the stack pointer is 5003, so -1. Okay, so the PC value will be stored in the stack, the top of the stack will be stored in the stack pointer. So in this program, for example, SP is having the value of 3503, then SP minus 1, we will store the higher byte value of PC. Higher byte value of PC is nothing but 46. This will be stored in PC minus 1. PC minus PC value is, sorry, SP value is 3503. So minus 1 in the sense 502, there 46 value will be stored. Then SP minus 2, which is nothing but where your PC lower byte value 02 will be stored. So at 3501, 0B value will be stored. Fine. So this is used to why we are storing the PC value in the stack means we have to return to the program where we have stopped the execution. So that's why the PC values are stored in the stack. Okay. So once it jumps, so it will execute the instructions. If it once the executions are over, at the end we will use the return instruction. This instruction is used for the processor to return back to the place where it has stopped the execution. Here it has stopped this execution at 4006.B. Fine. So it will return here. How it returns is, once the processor is executing this instruction, it will look on to the stack pointer to know the top of the stack where we have stored the PC value. Fine. So the PC value is stored in 502.46, 3501, 0B. So this value will be again feeder to the program counter. Okay. So once the process sees this program counter, it will return to the line where we have stopped the execution. So this is how the call instruction works. This is the unconditional call. So next we will call the we will see the conditional calls, which is similar as we have seen in the conditional and unconditional jump. So it will check to the condition whether it is satisfied or not. If it satisfies the condition, it will call that particular address that we have mentioned in the instruction, otherwise it won't. So such conditional call instructions are CC, which is nothing but call on carry, CNC, call on no carry, CP, call on positive, CM, call on minus, CPE, call on even parity, CPO, call on odd parity, CZ, call on 0, CNZ, call on non-zero. So these are all the conditional calls which work similar to that of conditional call, but it will similar to that of unconditional call, but here it will check the condition. If it satisfies the condition, it will jump, otherwise it won't. So the next branch instruction that we are going to see is restart. So which is nothing but RST. So we have 8 such instruction: RST0, RST1, RST2, RST3, RST4, RST5, RST6 and RST7. So like before, as call and jump, what you have used, so you have to call the address 4500, 5500. We have used like this. In the instruction itself, we have mentioned the address where we want to jump. But here in this case, RST0, RST1, we have predefined address. Okay, this was predefined. Once the processor executes this instruction, it will jump to the predefined address. So for RST0, the predefined address is 0000. For RST1 it is 0008. For RST2 it is 0010. 3 is 0018. 4 is 0020. 5 is 0028. 6 is 0030. For 7 is 0038. These addresses are predefined. So for example, if you have the instructions like this, fine. So and we have used this here, okay, so consider as 6. So then, so if processor executes this, when it happens to execute this instruction, automatically the PC value will be changed, okay, the PC value will be changed, that we discussed before itself. So it will jump to the address here, what the address 0030, okay. It will execute the lines whatever we have mentioned here, fine. These addresses are predefined. So how these addresses are defined in the sense, you have to multiply the reset number into 8. So this reset number is nothing but the number values that we have here, 0, 1, 2, 3, 4, 5, 6, 7. So here we have RST 6, no? So we have to multiply 6 into 8. So this multiplication is hexadecimal multiplication. That's why we have the value 30. So 0030. Fine. This multiplication is hexadecimal multiplication. Don't forget that. We will derive the number from the particular instructions number into 8. Fine. So that's all about the branch instructions. Next we will see about, so that's all about the branch instruction. Next we will see about the push and pop instructions. So if you want to enter a value into a stack, or if you want to get a value from a stack, we will use push and pop operations. So that you have already seen in data structures. So but here we are going to use those push and pop as an instruction itself, fine. So push is nothing but entering a value into a stack. Pop is getting a value from the stack. So first we will see about the push instruction. Okay. So the instruction that we have is push RP. So RP is nothing but register pair. So what are the register pairs that we have in the processor? You already know that we have seen in the architecture itself. Yes, yes, it is B, C, D, E and HL. Okay. So for example, if I take push B, so the pair for B is B and C. So what will happen is, it will push the value in B and C into the stack. Okay. So if this is your stack, okay, and the top of the stack value is mentioned in the stack pointer, assume it as so assume it as 4506, fine. Top of the stack value is 4506. So what will happen here is, so before execution, so B and C value would be 4A 5C. Okay, this is a 16-bit value, 4A 5C, that is resides in the B and C register. What will happen here is, the B value will be stored first, fine. So the how it is stored is SP minus 1, there your B value will be stored. SP value is 4506, okay, that minus 1 is 4505, 504, okay, that value is 4505. So in 4505 the B value will be stored, that value is 4A. So the C value will be stored in SP minus 2. SP minus 2 is 4504. 5C will be stored here. Fine. So again your stack pointer will be subtracted by 1 and will point to 4503. So the stack pointer will be updated with the value 4503. Fine. So how the push operation happens? It will subtract one value from the stack pointer, then it stores the register pair values one by one by subtracting the stack pointer value. So here for example I have taken register pair B and C. You can use D, E, HL also. If you use this, you have to change the instruction as push D, push H. Fine, this is how we have to use it. The next instruction is pop instruction. Pop is you are getting the value from the stack. So again here we are going to see about the register pair. Now we will use pop D. So the pair for D is E. So see, for example, stack pointer is having the value of 5000. The same value we will take, okay, 4506. So before execution, D and E might have some value, okay. This is your stack with the address 4 okay, with the address 4 6 7 8 9. So consider that you are having the value like this, okay, fine. So what will happen is the value in SP, so SP is nothing but 4504. The value in SP will be stored in E register, okay. The value in SP will be stored in E register and SP plus 1 will be stored in D register, okay. The value of SP is 4506, that value is 5C, that will be stored in E, plus 1 is 4507, that value is 6A, it will be stored in D, okay. So here if you see push and pop, in push first the address is decremented, then the value is entered into the address. So whereas in the pop, first the value has been taken and it is incremented, where in push it is decremented, in pop the address value is incremented. So first you are taking the lower byte, see here, first you are taking the lower byte value outside, then you are taking the higher byte value, fine. So this is of the push and pop instruction box. So this instruction is only for the stack and not for the memory that we have. So next we are going to see about input, output and machine control instructions. So first we will see about the machine control instruction. The first machine control instruction is EI, which is nothing but enable interrupt. When the processor executes this instruction, it will enable all the interrupts. So all the interrupts is nothing but all the hardware interrupts, okay, hardware interrupts. So how many hardware interrupts we have? That we have seen in the architecture itself. So it is 5 hardware interrupts, 5. So all those hardware interrupts will be enabled if we use this instruction, fine. Next instruction is DI, which is nothing but disable interrupt. So it is just opposite to enable. Here you are enabling all the interrupts, here it will disable all the interrupts, okay. Next instruction is NOP, which is nothing but no operation, okay. When your processor executes no operation instruction, the processor will remain idle for 4 clock cycles. So idle in the sense it won't perform any operations for that clock cycles. So for 4 clock cycles, the processor will remain idle, it won't perform any operations, fine. So that's for no operation. Next is halt, HALT, halt. So this instruction used to represent the end of the program, fine, okay. So next instruction is SIM, set interrupt mask. So this instruction is used to read the status of 7.1, 6.1 and 5.5 interrupts, okay. That is one purpose. Another purpose is to read the input serial data, okay. So the purpose of SIM is to read the status of these interrupts and to read the serial input data. Next instruction is RAM. RAM is nothing but read interrupt mask. So that this instruction is used to implement implement the interrupt 7.5, 6.5, 5.5. So there in sim we have read the status of the interrupt. Here we are implementing the interrupt, and then it is used to read the serial output data. So this is the purpose of RIM. Okay, fine. So that's all about machine control instructions. The instructions are RIM, SIM, no operation, halt, EI, DI. So next we will see about input output instructions. So these input output instructions are used to read the data from the peripheral device, or to write or give the data to the peripheral device. So as we have seen in the introductions class itself, I have told that peripheral devices might be your input devices or output devices, like your keyboard, monitor, mouse. These could be your input or output device for your processor in particular. Fine. So if you want to read a data from the input device, you are supposed to use in instruction. If you want to give a data to your output device like monitor, you are supposed to use out instruction. Okay, we will see it with an example. Okay, in is the instruction. With that you have to give the 8-bit address. Okay, so why it is 8-bit? This we have discussed in the feature itself. So one of the feature is that 2 power 8 will give you how many input output ports we have. So that is 256. So this is 8 is nothing but that we have I have said in the feature itself. This 8 is nothing but the address values, that means the total address, 8-bit address. Okay, fine. The each and every input output devices are addressed by using 8-bit values. But in case of memory, each and every memory location is addressed by using 16-bit values. Fine. But here in input output we are using 8-bit addresses. Fine. So the device that we connect with our processors, each and every devices will have an address. Those address is of 8-bit. If you want to fetch or get a value from the input device, you have to mention the address of that input device. Okay. For example, if I say that, so this is your processor, and this is your input device like mouse or keyboard. For example, I am saying if this address is 78, if you want to get a value from this, you have to mention it as input 78 H. So this H is nothing but hex value. Okay, fine. So once your process sees this instruction, what it will do is it will get the value from this port. This is nothing but port address. Fine. So to this port your input device is connected. So once your process sees this instruction, it will automatically get the value from this port and store in accumulator. Fine. So once it get the value from the 78 port, it will store that value in accumulator. That is in instruction. It will get the value from the peripheral device. So next, out. So again we will mention the same 8-bit address. Okay. So with this processor, if you have monitor for example, and this address is 8A, fine, you have to mention it as out 8A, which means that you are giving value to this monitor through the port 8A, because in the 8A port only your monitor is connected. Okay. If you want to give a value to this port, that value should be in accumulator. Okay. The value in accumulator is given to the port address. Fine. Okay. So can you all get how this input and output works? If you want to get a value from the input device, you have to mention the address of that input device. Fine. So that value will be automatically stored in the accumulator. Okay. If you want to send a data to the output device, there also you have to mention the output device address. The value that you have to transfer to the output device should be stored in the accumulator. So as of here, the in and out happens through the accumulator. Fine. So that's all about the instruction set of 8085 microprocessor. Maximum instructions we have covered. So what are the instruction sets we have seen? Data transfer instructions, which includes load, store, move, transfer, all those things. So second set is arithmetic instruction. There we have seen addition, subtraction, compare instructions. There we have seen about some of the addressing modes. Immediate value we have added, with the registers we have added, with the memory we have added. And the next instruction set is logical instructions. There we have seen OR, AND, XOR, complement, rotate, that is rotate left, rotate right, that we have seen. And next thing is branch instruction, that is conditional jump, unconditional jump, conditional call, unconditional call, reset. And the fifth one is push and pop instructions that we have used in stack. And last one is input output or machine control instructions. So in the next video lecture we will see about the timing diagram of 8085 microprocessor.